Hello, my name is Troy Keckley. I'm going to be talking today about computational fluid dynamics modeling of odor, kind of the next step towards the mythical odor goggles. A little bit of my background: I'm a division manager for a solid waste consulting firm, and part of my duties do involve the use of software and field studies to look at how odorous gases move from landfills and transfer stations out to surrounding communities. And I'm sure you're wondering, what is someone from the solid waste industry doing at a canine conference? Well, that's because I'm also certified and operational as an explosive detection canine handler for the Airport Police Department in Bozeman, Montana. And this gives me a unique perspective of not only the technical side of things, but also the operational. Now, what is computational fluid dynamics? Well, it's also called CFD, and it's just software that uses complex math to simulate and analyze fluid flows and heat transfers. And basically, for what we're doing for this work is simulating how the liquids and gases move and interact in this particular environment. Now, how many of you heard the phrases odor always rises and then falls, or odor always falls and then rises? I've heard both taught, and both are wrong because of one word: always. It makes it an absolute. The only time that word should be used is this: odor always moves. Now, how it moves depends on a lot of different variables, and CFD software can help us visualize that. Now, the objectives of this effort really is just to simulate real world conditions and how they affect the odorous gas movement in it, and then use the animation and images to help translate the complexity of odor movement down to the operational level. We do use software that's called SimFlow. There's a lot of different softwares out there, so this just happens to be the one we use. It is not a recommendation. It's just what we use. For the modeling, the odorant and source properties such as sublimation rate, and densities, and diffusion coefficients, they're all obtained from existing research, or I calculated them to the best of my ability. And then the visual limits in the models that you're going to see, and these are the visual limits of the odor, they're approximate, and they represent two orders of magnitude of concentration levels, with the low end being about 500 parts per trillion. But this can be adjusted for the desired level of concentration. In that, if I want to show the limit of odor is 1 parts per billion, well, I can set that visually in the model. And if multiple gases were sublimated from the source material, I use the dominant gas in the headspace for the physical properties of the modeling. And the models are based on real world events or hypothetical realistic situations, all for the purpose of evaluating that odor movement in different conditions. So, limitations and advantages of CFD modeling. First, the limitations is it's very time consuming, and part of that is because it takes a ridiculous amount of computer horsepower to process it. And this is not the kind of thing you're going to run on your basic laptop. It also can't account for all the variables, such as absorption of materials in that environment. But it does account for the primary variables that impact the overall movement and concentration levels. And the accuracy of the modeling does depend on the data that we're plugging into it and how detailed the model space is. And one of the issues we ran into is just accurate sublimation rates of some of these materials is hard to come by. And also, some of it are so low that the software struggled to process it properly. Now, the advantages, though, is that it allows repeated modeling to test different conditions. Okay, such as I can have the same situation and I can run the model, but then I can go in and change maybe the wind speed or the wind direction, or even the sublimation rate to simulate that maybe the source material is increasing or decreasing in temperature throughout the model time. And that just allows us more flexibility. And then from that, we can take visualization. So that's images and animations, it's pictures. Pictures speak much more clearly to the masses, to most people, than a chart with a bunch of numbers. Okay, and then when you combine those visualization tools and products with videography of actual training events, well, then you get a much clearer picture of what is really going on with regard to the odor movement. So, a couple examples today. First example is the unit training. So, it's the narcotics side. It was heroin, and I used acetic acid in the modeling. And it was a high height inside a cabinet inside the camper in the middle. It was a very windy day, And the odor raged for about 30 minutes, and then the teams started doing their search. And all the teams are veteran teams, live finds on the streets, and not a single dog showed a change in behavior. They all thought I punked them and didn't hide the source. I did, and I wanted to find out what was going on. So developed the model and ran it. And this is a cross section showing the magnitude of wind. So basically the wind velocities in the model space. And the oranges and the reds are high velocities, and the blues and the greens are low velocities. And you can see there's a pretty stark contrast, particularly at the top of the camper. And that contrast, that big differential in the velocities of the wind, create high and low pressure zones. Specifically, a low pressure zone right at the top of the camper where there's two roof vents. And really what we were seeing was Bernoulli's principle in full effect. That's just the equalization of pressure in a system. That means if there's a high pressure zone in a system, that wants to flow to any low pressure zones in the system. Okay, and so that's what it was doing. There was higher pressure inside the camper, and it was wanting to pull up to that low pressure zone through those roof vents. But there was another thing at play, and that's turbulence diffusion. And even though there was low wind velocities between the vehicles, there was a lot of turbulence that was just exacerbated by the handler and the dog going around them. And so those two things, the turbulence diffusion and the pressure differentials, caused it that the odor couldn't establish to a high enough concentration where the dog could detect it. And the modeling showed that. And you can see it basically being pulled out as the camper fills up with odor. It's being pulled out those roof vents. And note that there was a door on the side of the camper. You could see daylight through the gaps. That's in the model. Had no impact on the odor availability. And you could see that odor try to establish and get down lower to where the dog might detect it, but that turbulence diffusion prevented it. The next model we want to talk about is the influence of an HVAC system, ventilation system, so heating, ventilation, and air conditioning. And those of us in the bomb dog world, we understand this all too well. It's essentially mechanical movement of air. We're in those big stadiums and so forth where there's ceiling fans and ventilation running. And that's what this is simulating. It's just a large room, actual room, but simplified. And then 6 HVAC inlets, 2 return outlets. And the IED that I simulated, 2,4-DNT was the gas that was modeled. And the dog zone, you're going to see it just from the ground to 2 feet up. I figure that's where the dog's head is most of the time. So this first image just shows the limit of gas out to about a minute and a half. And this is just due to molecular diffusion. There's no ventilation system running. This is just the molecules bouncing off one another, emanating away from the source. This is the same time frame, but with the ventilation system turned on. And you look at this and you can see there's clear deformation compared to the last one. And maybe you're wondering, okay, what's the big deal? Well, this is the big deal. This is after 10 minutes. That odor's everywhere in high concentrations. So what does that look like from the dog's perspective? Well, we start running this out. It stays localized initially, but as the ventilation system keeps running, those low limits of the odor start moving further and further away. And you'll notice that the higher concentrations are following it out to where eventually you'll actually see, 2 orders of magnitude higher concentration about 30 feet away from the source over in that corner. Okay, that's an issue, and handlers need to be aware of that and how they plan out a search in these types of environments. Now, the last example is just a IED in a public parking lot. And so simulated a pipe bomb with smokeless powder. So diphenylamine was the primary gas. Dog zone's the same. And that's all we're going to look at. Is just looking at the dog zone. 5 minutes, low wind, 3 miles per hour. And you can see it kind of working under the vehicles, wrapping around some of the vehicles. But what I want us to look at is these areas of concentration downwind. The car next to it, that's easily order of magnitude high, level higher than the low limit. But then even 3 vehicles away between the cab of the pickup truck and the bed, that's almost an order of magnitude as well. So that's a factor. Now, what's next in this effort? Well, I'm going to continue modeling, trying to improve accuracy and realism. Hopefully collaboration with those of you in the science community and working with other handlers to improve frontline results. And then also just using the technology and knowledge to be a better trainer and handler myself and help anyone in the canine community achieve their goals. I thank you for your time. If you have any questions, please feel free to email me. It'll be easier for me to respond to an email or catch me during one of the breaks or throughout the conference. I thank you for your time and appreciate your attention.